Okay, so good afternoon, everyone. Thanks for attending this session. The presentation is on the use of finite element analysis for and assessing live load distribution for solid slab bridges for evaluation and design. And the work I'm going to present actually was done by two people. That's a project that ended a couple of years ago, and that are now, they were at Polytechnique before at that time, but now they are the contributories, professor at Laval University in Quebec City, and Patrick Thuret is a bridge engineer for a consulting firm in Montreal. So the presentation will be on the behavior of, we'll talk about the behavior of solid slab bridges and present the objective of bridge analysis for design and evaluation. And I will introduce or discuss about the multi-level analysis approach that I'm like to present and show a case study and conclude with some recommendation. So solid slabs are usually considered as very simple structures for design and evaluation, and it seems that since the structure looks simple, its behavior should be as simple. Actually, it's more complex. It has a more complex behavior than, for example, slab on girder bridges and stuff, for some instance. And when I'm saying slab bridges, although everything I'm going to present will be on slab supported on bearings, it's also, the conclusions also apply to slab type frame structures. So that an example is shown here. My interest actually came following the collapse of a bridge in Montreal, near Montreal, 15 years ago, that is due to the shear failure at the obtuse corner so that originated at this point here, the picture of which we see here. And that collapse caused the death of 5 people and injured 6 others. And following that, actually, I was in charge for the Quebec Ministry of Transports of finding the causes of that collapse. And further, since many of those bridges are on the road network, have had several research projects, some of which were experimental, others were analytical on the behavior of solid slab bridges, and 4 of those were tested to collapse with the objective of having a shear failure. So maybe, although it's not part of this presentation here, but I would say that slab type bridges are quite redundant structures, I should say, for at ultimate. And so nevertheless, so why am I saying that the behavior is complex? If we look at this very simple slab type bridge with 12 meter wide and 10 meter in span and a half a meter deep section. So, and if we look at the dead load only, then we see that there is a non-uniform support reaction, actually. And although we're assuming that sometimes we have a uniform support reaction for dead load, actually there's some corner effects, and the corner effects, I'll also do that later, that are real, actually. So, but very often it's neglected, and the cause of this corner effect is due to what is called anticlastic flexure, or call it double curvature in the bridge or in the deck, so that it tends to load the curvature in the other direction, that is due to the Poisson's ratio, tends to increase the load near the corners. So that was for a straight bridge. If I have a skewed geometry, and let's say here we have a 30 degree skewed bridge, then the effect is much higher. So you get that peak load at the obtuse corner here. And if we look at the magnitude of that, it's sometimes for the 30 degree skew bridge that I'm showing here, there's a magnification of more than 7 times the average shear effect. So it's only under dead load. So how can we show that? Actually, there are 2 effects. There's the Poisson's ratio effect, which is due to the classic or double curvature I mentioned before, which contributes for if you have a zero angle skew, then it can double the reaction. However, due to the skew angle, actually there's a magnification that can go to a very high value. And I would like just you to know that, for example, at 45 degree, the value we can go around 10 times the average. The corner effect can be up to 10 times the average value. And it is, in fact, was measured. This is a test that was done 1987, so that's more than 30 years ago, by Morrisons and Wesch. And in their test, they had a 45 angle skew angle, and they measured the reaction here. And we can see that in service condition, so in red, it's the obtuse corner here. The ratio is about 10, just a rough value about 10. And this kind of reaction, actually, or increase in shear near the obtuse corner, lasts until we get something like a nonlinear behavior, whereas the reaction at this point stops to increase, whereas the reaction on the other side and across the width here starts to increase as well. So its real was measured experimentally, and so it's not just due to the model, for example. Some people say, "Oh, it's a problem in the modeling." No, it's real. So if we're talking about the live load distribution and bridge analysis, so there are two types of several types of concerns for bridge design and bridge evaluation. But I would say that in the past, safety was the main issue, and cost was the second one, and service condition came to the third. Nowadays, it's more safety, service, and cost are usually the new trend in bridge construction and bridge rehabilitation. So if we do bridge design, so safety will usually something that is very well covered by code, and we make sure that the section remains ductile. And service conditions usually are taken care by selecting the adequate materials and appropriate details of like reinforcement cover and whatever is needed to increase service condition. And cost, assuming that the bridge type has been selected and the locations, so you have the choice by saying, do we use a cast in place or precast construction once the bridge type has been selected. So at the end, actually, there's a limited impact of refined analysis versus simplified methods in the design of new bridges. For bridge evaluation, safety is a different issue. It's been discussed lengthily today by other presenters, and so you have to identify all potential failure mechanism. You have to quantify the level of redundancy, determine the actual material strength, determine the realistic dead and live loads effect, and the service conditions are helping. Actually, it's what you see is what you get. So what you see helps you to understand the structure's behavior. So does it behave as predicted by the models or not? And the cost is mostly related to should we rehabilitate or replace the bridge. So a strong impact on cost is whatever you get from site investigation and the type of analysis that you are carrying out so that you can catch up the real behavior of the structure. So there's a learning process, and the learning process, if you take the University of Toronto engineering principle, and it's kind of a joke that from University of Toronto in structural engineering. So there are three rules: F equal to ma. You can't push on a rope, and you have to find an answer. You must know the answer. So that's kind of a tricky condition. So in analysis. For design, usually we would adopt linear elastic properties. And it's the same for most evaluation cases. Linear elastic properties are usually sufficient. However, in some cases in evaluation, you may go to nonlinear material properties. So what is the link between that and the University of Toronto principle? So to find an answer, you must first know the answer. So that's kind of an impossible way to do. There's no way to solve that. But I may add, this is my own creation. So if you don't know the answer, then you must find a way to find it. So and this is what I'm teaching to saying to my students. So there is you have to go from the simple model as possible, like simple static, simplified methods using the beam theory method, and it's so in design you have always to start with this. What I know from the young engineers, usually they want to jump on the computer, they want to do a 3D model, they use whatever software is available, and for them this is reality. So I think this is very important, even in design. Whatever methods are available or sophisticated softwares are, I think it's always important to start with a simplified method. In our bridge code, it's highly recommended. Then you can also use grillage analysis and often go to using finite element analysis, for example, using plate analysis. And we're talking here about slab type bridges. If you usually when you do bridge evaluation, you would proceed with the same 3 levels, and sometimes you may go up to also to do some field testing so that you have a better understanding on your structure's behavior. You can go even further in bridge evaluation, and you could use nonlinear methods such as yield line analysis, which is an upper bound analysis. You may also use nonlinear finite element analysis, and usually all those steps are usually sufficient so that to do a good bridge evaluation. You may also go to load testing, which is always an expensive activity, and go at the end, if needed, to proof loading, as some jurisdiction do once in a while. So this is some approaches that can be adapted. So I'm going to illustrate a few the behavior of slab type bridges using a simple span solid slab bridge example. So the work that I'm presenting here has been published about 10 years ago with the two co-authors of this presentation. That's their work. So it's mostly based on a 10-meter long structure, the 3 lanes structure, so it's 12-meter wide and a half a meter deep structure. We have 2 types of loading, and uniform load for dead load and the track. And we're using different type of linear finite element model, grillage, plate element, and solid 3D. And just to show you that when I say grillage, there's an orthogonal grillage, which is often recommended, but you'll see the conclusion, it's a very bad model. And the best grillage model, in which if you have a skewed geometry, so the traffic's from left to right, so your transverse element will be parallel to the structure support, which is the most optimal way to do a grillage, as I will show you later on. Just to show that if we're now looking at the uniform load for bending moment. So if we look at the bending moment, and this is for a straight geometry, here is for skewed geometry with 30 degrees. Let's focus on this one. So if you only use a plate element and you compute your bending moment, you won't get the right bending moment. You have to add, as it's required in the ACI code and most design codes, you must add the flexural bending moment and the torsional bending moment at each point, so that you get the real bending moment. It's what we get here. It's what we get the real bending moment here, and the line here with the red, the black points. The dash line here is what I call the non-orthogonal grillage model. So, and we got also the same answer using a plate element and. Actually, this is plate element. We're using solid element. If now we're looking at the reaction, we're still with the uniform load, the reaction. So this is, as I showed before, the corner effect due to, so this is the shear at support, and we see the corner effect and grillage model. Grillage model catches the the shear across the width, but it misses this increases. And it's the same if I have a 30-degree skew. So the grillage model is very good for shear across the width, except near the obtuse corner. Different truck loading here for one that is two that are for more bending moment, or the two others are more for shear. And again, if I look at the for bending moment, this is the plate element here. If I am adding mx plus my, and the non-orthogonal grillage model catches that very well. So it's a good approach. And if I'm looking for the same two cases now, but the loading cases, but I'm looking at the shear across the width. So if I have a straight configuration, the grillage model is quite good. However, if I have a skewed bridge, I'm missing the grillage model is not very good to catch this magnification factor on the side. And I'm doing the same here with a two loading condition for the straight bridge and skewed bridge, comparing the grillage model to the solid model. And again, it's very good, the grillage model on non-orthogonal grillage, to catch the load distribution across the width, except near the obtuse corner. So how critical are the shear force at the obtuse corner? So is it because we see that we don't want to do refined analysis, a very, very refined analysis all the time. So I'm going to show you two or some nonlinear analysis that were done, and we'll focus about the same bridge same bridge that we've been looking so far, so the 10-meter long bridge. And so here we're seeing this is nonlinear analysis, finite element analysis, and the 10-meter span is this one. So we start, and this is the straight geometry. So we start with we're showing here is the corner force factor. The dead load level is about here, and the factored load is about here, the factored design load. And we can see that this corner effect reduces significantly when cracking occurs in the slab. So toward reaching the failure of the bridge, and this one failed in bending. If we applied, instead of applying a uniform force, if we apply forces in bends, then we end up, because this is that would create a shear failure. So we can see here the shear failure in the finite element model, and the corner magnification factor, or the corner factor here, also reduces to a value, and actually if the failure occurred here, of about 1.2. Means that the force or the concentration, if the corner factor reduces when cracking occurs. That was for a straight bridge. For a skewed geometry, so this is a 30-degree with a uniform load, and 30-degree with the corner with the two bands. So again, we're coming to close to a value of 2 at ultimate. Let's say for shear, because this is a uniform load, so for shear with the band, then we're closer to a value that will be around 1.5. So as a conclusion, actually the recommendation for design, and so it would be that the analysis for dead and live loads, I suggest 2 levels. One, using a simple beam analogy or grillage method. So you can use either this, but as I mentioned before, the grillage is very good for shear, for bending moment, except for the shear concentration effect near the obtuse corner. In the Canadian code, we have 2 equations, one for simply supported condition, one for continuous supported condition. The effect is smaller when you have continuous support. So this factor increases shear forces in the obtuse corner, and the value that you would get with this equation would be close to what we get here. We observe in nonlinear modeling, and the same as Morrison's and Wesch test series, and this should be enough for most cases. If you have a structure, and whereas for design here, in which you're a bit uncomfortable with the shear stresses, then you may use plate model, a finite element plate model, just for the shear. For the combination of bending moment, it gets complicated because you have to add the flexural and the torsional effects at the same time. So grillage is enough for that. However, for shear, it may be helpful to use, recommended to use plate analysis to get the better shear effect. It's beyond the scope of this presentation today, but or the topic of the presentation, but we came to the conclusion that using very often we don't require to use reinforcement over the width of solid slab bridges, but it would be recommended to use either to lap the bars like this, to use a or like this, or to use a U-type stirrup like this on the one more slide to go, and you can also use something like this around the perimeter. And my last slide here. So for evaluation, I would say that 3 level could be used. So for bending, shear, and shear discrete support, then you can use a grillage model. And highly are also recommended to use plate analysis. And that, thank you for your attention, and I'm open for question.
Thank you, Bruno. Very interesting topic.